This video is going to cover step 2 in hypothesis testing structure. And I'm going to open up the document, and we're going to start by looking again at this rare event rule for inferential statistics. And we'll look at the wording again. If under a given assumption, the probability of a particular observed event is extremely small, we conclude that the assumption is probably not correct. The words I'm going to key on right here are a particular observed event. Well, that observed event is going to be a value of a test statistic that we are going to determine whether it's extremely small or not. So that's what we're looking at in step 2, is developing this test statistic. So if we go down to step 2, you recall then that we are going to be in chapter 8 looking at only 3 parameters. P, which is a proportion of successes in a population, and mu, the Greek letter, lowercase Greek letter m, mu as the mean of a population, and the Greek letter, lowercase Greek s, sigma, as the standard deviation of a population. And we're going to have a test statistic for each one of these. And you'll notice, or you'll recognize the test statistic when you look at the possible test statistics in 2 ways. One, it will say it's for a test of proportion, or test of mean, or test of standard deviation. And another, in the formula for the test statistic, and these are the formulas for the 3 parameters, testing the 3 parameters, you'll notice that in the test for proportion that we see the letter P. That is the population, the symbol for the population proportion. And when we talk about test of the mean, you'll notice that in the test statistic for the mean, you've got the Greek letter mu, mu. And when we talk about the standard deviation, you'll remember the population standard deviation is sigma. You'll see sigma in the equation. So you recognize it by it's telling you what parameter is being tested when it identifies the equation in, say, the formulas and tables handout. And you can look at the equation and the test statistic equation and see the population parameter in the formula for the statistic. And another important thing that I need you to remember is this, that the test statistic itself is a random variable. And if we're testing a proportion, the random variable value is z. It's a standard normal. If we're testing the mean, the random variable value, the test statistic value, is t. Do not confuse that with z or any other test statistic. It is t. T because we're testing the mean. And the reason we're using t instead of a z is because we don't know the population standard deviation, and we're using s, the sample standard deviation, instead of sigma in the formula. And when we are testing the standard deviation, the random variable for the test statistic is chi squared. It's another Greek letter, a new Greek letter, and it's chi. Sounds like a K-I. And but you need to make sure it has a square on it. It's chi squared, okay? It's kind of like a swishy X. Okay, so those are the formulas for the test statistics. And and the reason we're using these formulas is because they compare the parameter in the population that is being tested with the sample statistic which estimates that parameter. So when we're testing for proportion, in the formula for the test statistic, we've got p hat, which is an estimate of p. In the test of the mean, we've got x bar, which is an estimate of mu. And in the test of standard deviation, we've got S, which is the sample statistic estimate for sigma, okay? And it's making a comparison or comparing these two things. So let's talk about what happens when the assumed value of the parameter is true versus not true. When the assumed value of p, testing in proportion, when the assumed value of p is true, then p hat is a good estimate of the true parameter. It's going to be fairly small. It should be fairly close to p, so the difference is going to be small, and we would get small values of z. Okay, so the test statistic should be small. Before we go, let's take a peek at what the graphs of these test statistic values are. The z is standard normal, so it's the bell curve, and the mean is 0. T looks like a standard normal, and it's very close to a standard normal, but it is not z because we don't have sigma. We've only got the sample standard deviation, S, in there. But it's bell-shaped, and it also has a mean of 0. And chi-squared is a little bit different for a test of standard deviation because we're squaring S in here, we're squaring sigma in here. This is never going to be negative. So chi-squared values, possible values of chi-squared, start at 0 and go up to infinity. And the mean of a chi-squared is not 0. It starts at 0. The mean of the chi-squared is n minus 1. Sample size minus 1. So going back to the relationship between the sample statistic and the parameter, if the parameter is true, if p is true, the assumed value is true, then p hat is going to be close to p, and this is going to be small. So we should get values of z in close to 0. However, if p is not true, in other words, our assumption is false, p hat is looking at the true parameter p, and so it's very likely that it's going to be very substantially different from the assumed value, and therefore this is going to be large, making z large. A large in the positive direction if p hat is bigger than p, large in the negative direction if p hat is less than p. So we're liable to get p hat values out here in the tails. One of the tails, we're liable to get a z value in one of the tails if the assumption is false, okay? Similarly, for the t, we've got a difference here. If mu, the assumed value of mu is true, x bar is going to be a good estimate of that, and we should get small values for t, because these are going to be close together, and the difference is going to be small, which puts the value of t close to 0, closer to 0, and in this region here. But if the assumed value of mu is different from the true value, x bar is estimating the true value of mu, and it's liable to be substantially different than the assumed value. Remember, the assumed value is being used in the formula right here. So we're liable to get large differences here, which means t is large. If x bar is less than mu, t would be negative. If x bar is greater than mu, t would be positive. So if the assumed value of mu is not correct, then we're liable to get values of t out in one of the tails, okay? Not in the middle. And similarly for the chi-squared, we don't have a difference now, we have a ratio instead. And if sigma, the assumed value of sigma is true, then S is going to be, or actually we do it, we'll talk about it this way. If the assumed value of sigma is true, then sigma squared is going to be assumed to be the true sigma squared. And S squared is going to be a good estimate of sigma squared. So if the assumed value of sigma is true, then S squared is going to be about the same, or close to being the same as sigma squared. Might be a slightly smaller, might be slightly larger, but close to sigma squared, which means that this ratio, S squared over sigma squared, is going to be close to 1. And that means 1 times n minus 1 would be n minus 1. So the value of chi squared is going to be close to n minus 1. And we would get values of chi squared, the test statistic, in and around here. But if sigma the assumed value of sigma is not correct, S squared is estimating sigma squared, a different sigma squared, the true sigma squared. And so it may be significantly different and significantly larger than sigma squared, or significantly smaller than sigma squared, in which case this ratio is bigger than 1, significantly bigger than 1, or significantly smaller than 1. So our values of chi squared are going to be significantly larger than n minus 1 out here, or significantly smaller than n minus 1 down here, or again in the tails. And that's why we're using these formulas right here for the test statistics to come up with that observed value that we're going to determine if it's unlikely or not. So I'm going to end this here, and the next video is going to determine how to determine what the parameter is that's being tested, and which formula to use, and how we find the value of the formula.